So like I said, simple one-way ANOVA is comparing groups by an independent variable on a dependent variable. I don't know if that's clear, but what we mean is that we're going to compare groups by whether it's a predictor, it's a grouping, or it's a treatment versus intervention, and we're going to compare their scores on the dependent variable. So that dependent variable will be an outcome variable. That's a variable of interest that we want to look at. So for example, we want to look at the depressive symptoms by gender. Which one is the IV and which one is the DV?
Gender is IV, depressive DV?
Yes, exactly. And so if we're comparing anxiety levels by treatment modality, by whether they're using getting CBT versus psychodynamic. Is psychodynamic the IV or the DV?
IV.
IV. Okay, so that's clear. So next, want to talk a little bit about how ANOVA is different from regression, chi-square, and t-test. I think I briefly touched on this in the past. So ANOVA is different from regression, and actually regression, ANOVA is a special form of regression. So ANOVA is when the IV is categorical. So for ANOVA, the IV has to be categorical. So we're comparing groups. So if it was like just like a continuous, that wouldn't be, we wouldn't have groups unless we make it dichotomous. Like above 35 points, we say they're in this high certain variable group and below in the low group. So that's a main difference between ANOVA and regression, while the IV of regression can be either continuous or categorical. Believe it or not, I think when I learned my ANOVA class, I was with a very old school professor. He used a textbook that was no longer in print, so we had to buy it from the bookstore that was photocopied, and it was I think typed in APA style, something like that. And he taught ANOVA as a special form of regression. And so all we did, we learned regression, but the special form of regression, and we calculated ANOVA as we would calculate regression. I didn't appreciate that because it didn't link with my knowledge about SPSS. I just felt I learned another thing, another way of calculating ANOVA. But when I was running SPSS, it was totally a different story. So it just reminded me of when I talked about ANOVA is a special case of regression. Okay, so that's the difference between ANOVA and regression. And ANOVA in chi-square, the difference is that the dependent variable of ANOVA is continuous, like levels of depressive symptoms, anxiety levels, so that's continuous, you get a score. And then if the DV, if we change it to categorical, whether you're diagnosed as major depression or not based on DSM-5, then it becomes a chi-square question. So we're no longer comparing means of their depression scores because their depression scores are either depression or no depression. So we're comparing the distribution or the percentage of each group in the depression group versus the non-depression group. I'll give you an example following this. And then third, t-test and ANOVA, they differ in terms of t-test is limited to 2 levels or 2 groups of the IV. So in other words, we can only have 2 groups, men, women, comparing them on a certain outcome variable. If we have men, women, transgendered folks, then it's 3 groups, so we can no longer use t-test, and we use ANOVA. And if you use ANOVA to run 2 groups, you get the significant level results are identical with t-test. So in SPSS, you can choose what to do. So a lot of times, I never run t-test. I just run ANOVAs, even if it's with 2 groups. So I get identical results. But technically, you can just do a t-test when it's 2 groups. Clear so far? Okay, so I'm going to go over some basic concepts related to ANOVA. So how many of you know what ANOVA means, stands for?
Analysis of variance.
Yeah, so we analyze variance. Why is variance so important? What is variance? That's a good question and a tough one. It took me a while to understand, and I think it many years, and I think I understand now as I'm teaching, have taught this a few times. But we talk about variance a lot. We talk about mean and variance. Mean, we kind of know what's mean, right? It's very clear, like average, where the average is at. But variance, oh, we kind of know. It's like house bread, like variance, if it's more varied or not. That's sort of what we know. But why is it so important, and why is ANOVA all about analyzing variance? What is it about variance that's important? So this is how the textbook defines ANOVA. It's a yardstick to see if the systematic differences between two groups are significant enough compared to random variability. Clear or yeah, not sure what it means. Okay, not so sure. I wouldn't know either. Okay, so this is how we're going to break it down. So let's go back to the question of stats performance or stat grade or exam grade. So if your stats grade, we use Y. It's a combination or a function of three different factors. So one is the overall mean of everyone's stats grade. Okay, that's this mu is the mean. And then the second one is the effect of the IB. So for example, if we're wanting to know whether using textbook A versus textbook B, which one yields better stats grade. So one is the function of which textbook you are assigned to, which group you are assigned to. So if textbook A is a superior textbook, you would get some positive points here. Okay, and then the third part is error. This error is not like error in terms of mistakes, incorrect stuff. It's random error. It's random factors. Oftentimes, you'll hear a lot of, I don't know why they use the term error, but sometimes stats people frustrate me. I think when I was learning stats, you would read all the time about error. And I think for some of you who know I do research on perfectionism, and I am a perfectionist myself, reading about error, I'm like, I don't want to calculate this error, that's incorrect. It just bugs me. But later on I realized, okay, error doesn't really mean mistakes or failures. It means that it's the result of random things that are beyond the factor or the variable that we're interested in. So beyond the IB. So for example, so my score on a stats exam is a function of the overall mean and plus or minus the textbook effect. Like, okay, if I got textbook A, maybe I was more likely to get 2 points more. If I was in the textbook B condition, it would be -2, less likely to get, I would get a lower score because textbook B is not as good. And then E is the random other factors that are related to my performance. It could be related to my GRE scores, like how well I am with verbal. It could be related to the amount of time I studied, or like what the time of the class, whether it was a morning class, afternoon class, or related to the instructor quality, etc.
Can error be undefined?
Yes,
Okay.
it is. We don't know what it is.
Okay.
So it's the unknown.
Gotcha.
It's the unknown thing that could be related to all this.
Okay.
And so it's definitely, I think it's undefined. We don't know what it is. Yeah, great, good term. So in the future, I'll say undefined beyond the
Do you like it?
So this is why, this is the essence of ANOVA. And why is variance important? Because if there was no variance in stat grade, everyone got 100 points, would we be interested in what factors predict better stats graders or not? No, because everyone's the same. There's nothing to predict because results is everyone is going to get 100 points. So it's when things vary that we start to be interested. Why do certain students perform better than others? Why do certain athletes run faster than others? So it's when there's variance, we start to get interested in what factors these kind of difference. And of course, the outcome variable would be something we're interested in terms of decrease in anxiety scores after treatment. So if everyone decreased exactly the same, there would be no need to calculate. Michelle, do you have a question?
Yeah, so it seems like you're saying variance is like difference.
Yes.
And our goal is to try to, or one of the goals is to try to help understand that difference.
Yes, yes. What factors
Yeah, what factors
contribute to
are
the
accounting for the
difference?
difference that we're seeing.
Exactly. Okay, so another aspect of ANOVA is we're using a sample to predict the population. So I think I talked a little bit about that. So if I'm doing an exam or a research question on the class, I'm more interested in generalizing it. Like, is textbook A a better textbook than textbook B? Not so much. I'm partially interested in the class, 8 people, but the ultimate goal is to generalize it. I think, like when we do research study, is psychodynamic better than cognitive behavioral? If it's just specific to that 200 sample, we wouldn't be interested in it, because we would say that's just specific to them. I'm seeing a client that's not part of that 200 people, so I don't know. But the goal is to generalize, saying, okay, psychodynamic is better at treating trauma than CBT. Maybe, I'm just saying. And then to say, okay, so if we work with a trauma client, it might be good to refer them to a psychodynamic. I'm just, yeah. So we're using a sample to predict the population. So we don't know the real means in the population. So there's no way that I could get every data on every client that has trauma past, that has been seen by a psychodynamic therapist. And then every client in history that's been seen by a CBT, because that's what we're trying to infer to. So there's no way we can get the whole population, so we just pull out some sample and then use results from the sample to see if there's a mean difference and infer that to the population, to our research, to answer our research question. Clear? Okay. Okay, and whether we get significance in terms of test, F-test significance, it depends on these factors, and I think we've mentioned a little bit of that. One is the size of difference between the group means. So if they varied more largely, then we're likely to detect difference versus if they were closely together. And sample size in each group. If there were larger sample sizes, we would get it would be more easier for us to say there is a significant difference between the means. Because if there's only a small difference, if you have a large sample size, it would be easier to, you would more likely infer that there is a difference. Okay, so I think I gave an example of having a 10,000, sample size of 10,000 students, right? And it only explained 1%. So for example, if I had a huge sample and I said, okay, textbook A is better than textbook B in terms of performing in stats exams. Okay, and then you ask, like, how much better is it? Okay, it'll impact 1% of your grade. So, and you spend $150 more. Would you want to do that? Maybe not so much. But if it says like it impacts 50% of your performance on exams, okay, maybe it's worth considering. So the effect size is also another construct that we will talk about more so later on, is that significance is not the full answer. Significance tells you, is there a significant difference, but it is also related to the sample size. And so we want to also know how large is the significance, how large is the difference, and that's effect size. And the last one is the variance of dependent variables. So if the variance is smaller, we're more likely to get significance. So these are all the basic concepts related to ANOVA. And so our goal today is we're going to calculate an F. So ANOVAs are usually expressed in F tests. So this is an example from Crosby and Varela, 2014. So what this study did was they examined preferences for religious help seeking across different ethnic groups. So what they found is that there was a main effect for race on preference for religious help seeking. And they reported an F of 10.52, which translates into a p-value less than 0.001. And F within the parentheses are the 2 degrees of freedom, 2 and 383. So this is a key in terms of what you report in ANOVA. So if you're gonna write up a number results, make sure you have the F, the p-value. In the partial eta square here, this is the effect size. So I talked about it could be significant, but it has a large sample size. So using the partial eta square, this is where we get a sense of the effect size. How big is the difference? And so they further interpret, because there's 3 groups, African Americans, Caucasians, and Hispanic Latinos. So they further interpret which group is large, has higher scores than others. So they found that African American participants had significant higher scores on preference for religious help seeking than Caucasian and Hispanic Latino participants. So this is how you'll write up statistics related to ANOVA. And here are, I'm going to explain some key statistical terms. So variance, sum of square, degree of freedom. Okay, so variance is how widely varied our set of numbers. And so for example, if these are 2 sets of stats exam scores from 5 different students, which one do you think have a larger variance by eye volume? Second? Yeah, clear. It's clear that this is more varied. And so next I'm going to talk about degrees of freedom. How many of you are pretty comfortable with degrees of freedom, understand what it is? Okay, I see a hand and then I'm not so sure. Okay, degrees of freedom, it confuses me. It takes a while. I don't know how many times I heard about it, but it's just something I find and I write. And so I hope I can explain it. So I took a lot of effort looking up different definitions. So this is what I found. The number of independent pieces of information on which the estimate is based. Now you understand it, right? Of course not. I don't understand it either.
Thank you.
Okay, so another definition, which might be a little bit easier. The number of numbers that are free to vary when calculating a statistic before being forced to choose the last fixed number. Okay, maybe a little bit clearer, but definitely
I
not.
don't get that last part.
Huh? Not so much. Okay, so let's use an example. So if we had a test that was scored between 5 to 15, okay, and then we said that we had 5 students and they had a mean score of 10. Okay, so we're going to try to figure out what their scores are. So for a first student, Nate, give us a number, a score between 5 to 15.
12.
12. Okay, so the first student scored 12. Okay, the second student, Lauren. 7. Okay, so the second student scored 7 points. And the third student, Mary. 5. Okay. Okay, so we have 12, 7, and 5. So we have, what's the total now? 12, 7,
24.
24, right? And their mean is 10. So if we want them to have a mean of 10, how much should their sum add up to? 40, right?
40. Oh, 5.
4 people.
4. I thought there was 5 people. My bad.
Aren't there 3 people?
What? No.
Okay,
Oh.
4 students.
Oh, yeah.
4
40.
students, 40, and then we have 24 now. So the last student, if I ask Christina, like, give me a number. So,
Extra credit?
yeah, so what would the last student's grades be?
Would have to be 16.
16 is beyond, so, okay, they got extra credit.
Yeah.
Okay, so that's how they got a mean score of 10. Okay, so in this example, how many people were able to freely estimate the scores? 3, right? When it came to Christina, no, she can't estimate it freely estimate, you have to go with a fixed score to get the sum of 40. So we have 3 degrees of freedom here. So 3 pieces of information that was allowed to be freely estimated. Does that make better sense of what's degree of freedom? Okay. So I'll give you another example. So we have 5 children. Their mean weight is 100 pounds. What would be the total sum of these 5 children's weight be? 500. And so, how many numbers of weights are we able to freely vary? 4. Okay, yeah, so we have 4 degrees of freedom here. And we're estimating a mean with 5 participants. So, I talked about F value. So F ratio is the goal, or the thing that we're gonna, our end product today, when we're gonna calculate ANOVA. So I'm gonna give you a conceptual idea of what F ratio is, and then we'll later talk about how to calculate it. So the conceptual idea is, we talked about your score is a function of the total mean, the population mean, plus the effect of the IV, let's say textbook, and then all the other unidentifiable factors. So it's a factor of these things. Okay, so the F ratio is the ratio between the treatment and the error together divided by the error. Does that make sense? Okay, so it is like the influence of the treatment, or the variance of the treatment and the error divided by the variance of the error. Okay, so in other words, how much larger is the variability due to treatment plus error than simply error? Okay, if we have a larger F, like the variability of one scores is way more larger because of this than this, would it indicate that there's a stronger significant difference, IV effect, or a weaker IV effect? So when we're calculating ANOVA, we're gonna deal with sum of squares. So in that music, we heard sum of squares. So you divide it by the mean, and you deviate, you minus it with the mean, and then you square it, and then you sum them all together. So that's the sum of squares. There's going to be 2 types of sum of squares. One is sum of squares between groups, and one is sum of squares within groups. So sum of squares between groups, it would be the difference between 2 groups. We're trying to look at difference between 2 groups. Okay, and then the sum of squares within group is how much people differ within their specific group. So that would be like the variance that I mentioned, like the scores of textbook A, how much they varied, versus textbook B, how much they varied. And then the mean scores across textbook A and B, that would be more like how much is varied between the groups. So I'm still at the conceptual point. So I will tell you how to calculate it later. But so we will look at the sum of squares between groups, sum of squares within group. And there's also a total sum of squares, which would be these 2 added up together. And when we're going to calculate the sum of squares, what we use is that we will use each individual score and deviate that, or minus it by the grand mean, and then square it, sum it, we will get the total sum of squares. And if we use the difference between the group mean and the grand mean, then we can use that to calculate the between group sum of squares. And if we use each individual scores, how they deviate from their own group mean, that's how we calculate the sum of squares within group. Okay, so we'll talk more about how to calculate it. Want to give you a conceptual sense. And then here we also will be dealing with degrees of freedom. So there's going to be 3 degrees of freedom. One is the total degree of freedom, and this will equal the total sample size minus 1. So just like what Chris said, okay, you plus one, you get the sample size. Okay, and then we're gonna have between group freedom, degree of freedom. And what's the degree of freedom between group? It's the number of groups minus one. So if we have two groups, men and women, what's the degree of freedom?
One.
One, yeah, two minus one. If we have three groups, psychodynamic, CBT, control group, so the degree of freedom would be two. Okay, and the third degree of freedom is the degree of freedom within group. And that's calculated by the total sample size n minus a. Okay, and then this two will add up to n minus one. Okay, so we're gonna use sum of squares and degrees of freedom to calculate f. So what we will do is we will calculate a mean square. So divide the sum of square by the corresponding degrees of freedom, we will get a mean square. We'll do the same for between group and within group. So we'll get two mean squares, and then we will look at the ratio between the mean square of between groups divided by the mean square of within group. That'll give us the f value.